Allocation problems. This is a table of workers and tasks, and it's going to serve us as a reminder of how we attack the simple type of allocation problems. First thing we do is we look at the row and we say, well, person A will take at least 31 to do these jobs, so we subtract 31 from all of those numbers to leave 3, 4 and 0. Should have used a different colour. Anyway, person B will take at least 26 for whatever he does, so let's subtract 26 from all of these, like that, and subtract 30 from the ones at the bottom. Basically, you take the smallest number from all the other numbers. And now we'll repeat the same process for the columns. This is called row reduction and column reduction. Now, if there's already a 0 there, as there is here, we can't do anything. The second column, we can subtract 4. Now it's almost impossible to read. And the third column, there is already a 0 there, so we can't do anything, or we subtract 0, whatever you think. And now our task is to try to cover the zeros in as few as possible straight lines. And I can do it in 2 straight lines like that. If you can't do it in fewer than 3 in this case, because there's 3 rows and 3 columns, you can always do it in 3, just 3 vertical lines or 3 horizontal lines, whichever. So if you can do it in fewer than 3, then you're not finished. And what you do then, it doesn't matter how you cover it in 2 lines. I've done it in the best way, but it doesn't matter if there's alternative ways. You always do the same thing, and that is to look at the other remaining numbers 1, 1, 3 and 2 and reduce those numbers in the same way that we have the others. So we take 1, 0, 1 becomes 0, take 1 off that and take 1 off that, and we add 1 to anything that is crossed twice. There's only one number here crossed twice, so we add 1 to the 3 to make 4. So now we've got this table. If I put in all of the remaining zeros in red so we can see them maybe a bit better, we've now got this new table, and in blue I'm going to cover the red zeros with as few vertical and horizontal lines as possible, and we should see here that we cannot do it in fewer than 3, so I'm not even going to attempt it. What that serves to show is that we can now choose a 0 from each row and each column, like that. So 1 0 in each row, 1 0 in each column, 3 zeros in total, and those are the positions of the allocation. So we allocate task Z to A, task Y to B, and task X to C, and the times that they take, or the cost, whatever this is talking about, is found by just adding up the original numbers. So the 30 here is the original number, plus the next one I think says 34, can't read it properly, 31 I'm told, and the next one also says 31, so the total there is 92, and that's the minimum. And now there's problems. What if, like in this new table taken from page 45 of the textbook, I've changed the letters and words, what if some people just refuse to do things, like in this case I think Dennis is refusing to, or can't cook for a Chinese restaurant. How do we deal with that? Well, what we do is we sort of fill in a made up time. So if these are sort of the charges that people make for working in certain places, and we want to minimise those charges, then we know that A can't do W. So to use the algorithm, we sort of invent a number which is so big that we're never going to use it anyway. And what we do is by essentially just taking one of the largest entries in the table to get an idea of what a big number would be. 40 is about the biggest number here, I think, at first glance. And we sort of find a number which is at least double that, perhaps 3 times that, and whatever a nice number would be. In this case, 100 would do pretty well. So what we're saying here, we know we're never going to use these hundreds. We've made them so big that they're never going to actually be used in the optimum solution. And then we continue as before by reducing the rows, reducing the columns, and so on. And we end up with our table like this. Now we try and cross the zeros with as few lines as possible, and I can see I can do that with 2 lines here and here. Now we reduce the numbers which aren't covered. The smallest of those numbers is the 3, this 3 here, so we reduce the numbers by 3. and add 3 to the number which is covered once, only one of those in this case. And now in black I'm going to cover the red zeros, and it's a blooming mess, but all the zeros I'm now going to try and cover, just fill in where the numbers I've missed off are. All the zeros I'm going to try and cover with as few straight lines as possible. It's now possible to do that with 3 straight lines, so I'll add another one there, and I'll repeat that and we'll finish with the solution. I won't actually bother doing that. Now, what if we've got more people than tasks? So here we've got, this is taken from question 3 on page 44, more people than tasks. If that's the case, we invent a new task which we know is never going to happen, and if it's never going to happen, then we just put times 0 for it, and then we carry on as normal. So we reduce the rows, it's already been done, there's 0 already there. Reduce the columns, this column obviously already has zeros there, and then cover the zeros and just exactly as normal. Whoever actually gets task U, whoever gets allocated task U, is the person who in reality doesn't do anything. I've missed off the numbers here because I'm not actually going to solve this problem, but you get the message, I think. Now the question that we haven't yet looked at is, what if you want to maximise the numbers? Let's say that this is somehow 4 people, 4 things that we could sell, this is who we could sell them to, and we want to maximise our profit. So we want to use the big numbers this time. Well, a simple way, we don't change the algorithm. What we do is we change the numbers. Instead of maximising the numbers, what we do is we pretend that everyone's paid 40 quid. That everyone's paid 40 quid, and we look at how much change we'd give them. So this person, if they paid 40 quid and they're giving us 12, then we'd give them 28 change. This person would give 17 change from 40. This one 25 change, and so on. And now with the blue numbers we want to make the change as small as possible, and so we just solve the usual problem, Hungarian algorithm on the blue numbers. We reduce the blue rows, ignore the reds totally now, reduce the blue rows, reduce the blue columns, cover the zeros, reduce what's not covered, add what is covered twice, and whatever, the usual routine. And finally, it might be better for you to just read what's in the textbook about, have a look at formulating a linear program for these problems, and have a look at doing the same thing for transportation. You'll see it is actually very easy. Sean can do it already anyway. It's page 52 onwards.